Now, let's start with a brief history of the diode. A diode is a device through which the electricity can flow in one direction. So in 1939, the vacuum tubes were state-of-the-art in radio equipment. Only with the discovery of the semiconductor silicon p-n junction did the development of the electronic industry start to celebrate. A semiconductor diode is made of two different type of semiconductors next to each other. The junction between two materials gives the diode a special characteristic that has turned out to be crucial for daily lives. So the characteristic of two most useful semiconductor diodes like silicon and germanium are investigated in the following experiments. So diodes are basically unidirectional semiconductor. When you say semiconductor, it has a resistivity in between a conductor and insulator. As you can see here, the resistivity of the conductors is from 10 to the negative 8 until up to 10 to the negative 4. And also the insulator, the resistance, the resistivity is very high from 10 to the 6th power to 10 to the 18th power. These are the insulators. So in between these two characteristics is the semiconductor. Okay, when we talk about resistance in electrical term, is the ability of the material to oppose the flow of current. Now, let us try to start with a characteristic of an ideal diode. When we say ideal diode, it's referring to a diode that has a forward bias. When it is forward bias, okay, it's like a switch that it is closed. So it is a closed switch. Okay, when this is forward bias. When it is reverse bias, like here, this is the positive, you put negative here, and this will become an open circuit, so the current cannot flow. The diode current is zero. Okay, so there is what you call threshold voltage in dealing with diode. If we talk about ideal diode, we don't consider the threshold voltage. But in reality, there's no such thing as ideal diodes. It is only used just for analysis and comparison. So we have in industry a silicon diode and germanium diode. The threshold voltage for the silicon diode is 0.7, meaning before the diode will be closed, it needs a threshold voltage of 0.7, and a germanium requires a 0.3 volts before it will become closed. Now, what is the difference? Why is it? Why not the same? Why silicon has 0.7? Why germanium has 0.3? What is the reason behind that? Well, if you look at the structure, atomic structure of the silicon, if you compare the atomic structure of the silicon and germanium, look at this is the germanium here. Okay, this germanium, look at the outermost layer, it's far away from the nucleus. So that means the behavior of the orbiting electrons here is it will easily give off. So here, this is the atomic structure for the silicon. Okay, it is near to the nucleus. That's why it's little bit harder for the outermost orbiting electron to give off. So the more distance the electron from the nucleus, the higher the energy state. So it is the electrons can easily give up here. Okay, can easily move. So now, if we put an extrinsic material just like boron, it will attract the electrons from this silicon, just like here. This is an extrinsic material such as boron, or we can use phosphorus. Okay, this is the N-type material and P-type material. This is actually what you call the process of doping. Okay, this is the process of doping by adding donors or acceptors of atom to semiconductors. Atom is called the doping process. This is how the diode is being fabricated. As you can see here, these are the silicons, and they put an antimony or antimony has been added. So the characteristic of antimony is that the outermost shell, it has a atomic number of 51. So it will share some electrons. It is sharing some electrons when added together. So this is on this part we are making an n-type material. Okay, and this part we are making when added boron is added to silicon, same component silicon, it will become a p-type material. Okay, p-type material. So we have an n-type material and p-type material. When we say n-type material, the majority carrier is the are negative. Okay, and the p-type material, the majority carrier here are the positive. So this is n-type and p-type material. Now to form a diode, we need to, it is combined together, and this is the anode or the positive side, and the cathode or the negative side. This side is negative. So in actual diode, this is how it looks. So this is the positive, this is the negative. This line means here indicates negative. This line here, this gray line around the diode is negative. This one also, the black line is negative. This is how the diode that we are going to use in the lab. Now, there is actually, as you know, we talk about the threshold voltage, so we talk about the diode biasing. Suppose there is no bias, what happened inside the diode is that all the holes here and the electrons here will be, or the negative carriers here will be attracted to each other. It will form a depletion region. Okay? So, if there is a depletion region here, there will be no current flow. Okay? There is no current flow because there is no applied bias. There is a depletion region at this point. Now, what if we put a reverse bias? Let's say this is the positive terminal. This is N, but it is connected to a positive source. This is the N, negative. This is positive, but it's connected to a negative source. So what will happen? The depletion region will become thicker. So it's very difficult for any electrons to pass through this region. It's very, very heavy. Okay? Because it is the reverse bias condition of the diode. But if you put the correct polarity, so this is the P junction and the N junction of the diode. If you put positive here, negative here, and what will happen? The depletion region will be reduced and allowing some electrons to pass. Okay, so the electron flow will be on this direction. The electron, and the current flow is on the other direction. The current flow is opposite to the flow of electron. Now, we talk about half wave rectifier. This is the source. This is the source, the waveform of the source. This is the waveform of BR here, the voltage across this resistor. Okay. Now, let us try to analyze so this voltage is increasing with respect to time, right? So when the voltage is zero, up to less than 0.7, there is no, what happened to this switch? From 0 up to near 0.7, let's say less than 0.7, the diode condition here is open, right? This is open. So the diode condition here is open. So when there is open, what output can we obtain here? We are not getting any output. No output because no current flow here. The current cannot pass, right? So if it cannot pass the voltage here, we will not have any output. So this line here, you can see this small line here. It shows that the voltage is from 0 up to this point here. This point here is the 0.7. When it reaches 0.7 here, the diode start to close. The switch here, right, started to close, and then it will start to flow a current, and then if there is current flowing here, we will have an output. So at this point here, so there's a, it's like there's a point, I will just to make it, just to exaggerate this portion. At this point here, there is no output. Until for this point, it will start to go up. So at this point here, start to go up. This one is the output, right? And then at this point, it will go to up to maximum. Why? Because it is at the positive cycle. This is the positive cycle. It will be reflected to the output of the resistor. And then at this point here, where the voltage is going down from 0.7, it's going down. What will happen? There, the diode will again open. So there will be no output. So at the whole cycle, at the negative cycle, it will not be reflected in the output. This is the output. This is the source. Okay? There will be no output on this portion because it is on the negative cycle. At the negative cycle, the diode here is open. Right? The diode is open. So until at this point, okay, 0, and then it will reach again 0.7. At 0.7, it will start to go up. That means whatever voltage reflected here will be measured from the output side. So it becomes a cycle. So this is called half-wave rectifier. Okay. Now let's go for a full wave rectification. Oh, okay. Now, before we do that, let us go for the voltage across the diode. Okay. Let us, since they are in series, we can interchange the position. We put the diode here, and we put the resistor here. We can interchange, right? Because if they are in series, we can change the position. Now look at the voltage across the diode. This one here, we are monitoring the voltage across the diode. If we want to measure this is our oscilloscope. Okay, this is actually our source is from function generator. This is our oscilloscope, channel 1, channel 2. Of course, channel 1 here. Okay. Here I will connect it, this one here, sorry. This is the ground, consider as the ground. This is the red of the oscilloscope. This is the black of the oscilloscope of the source. Okay. So now this is channel 1. This is channel 1. And channel 2, of course, the ground of channel 2 will be here. The black of channel 2 and the red of channel 2 will be connected here. In this case, we are measuring the voltage across the diode. Okay. When the diode is open, so let me just draw it here. This is our source. The diode is open. Okay. And this is our scope, channel 2, we connected here. We connected here. Okay. If the diode is open, whatever the voltage here will be reflected directly on the scope. So if this is open, right? If this is open, it will reflect. So let us say, in this condition, from 0 to 0.7, what's the condition of the diode? 0 to less than 0.7. This is open, right? At that point, okay, at that point, it can register the waveform here. Okay, so this is our source, started to go up, less than 0.0. So this portion here, less than 0.7, this portion here will be reflected on the output of the diode. We can measure it. So here it will reflect there. It will reflect. Okay, this is the screen. And when it reached 0.7, the diode started to close, right? So the diode started to close. What will happen? So there will be, if it is shorted here, there will be no voltage reading. So if there's no voltage reading, at the full time here, this is the entire time. This is the time where the value of the source is more than 0.7. The diode is closed here, so it will be 0 here. You will have a plot here. There will be no output here on the diode because this is short. It's like let's say for example, you have a voltmeter. Okay, this is your resistor. Okay, if it is shorted here, then you measure the voltage here and then the meter here. What you can measure if it is shorted, it is 0. That's why here it's a flat line. And at this point, from 0.7 less than 0.7, again the diode here will open. What's the condition of the diode at this point now? It will open. So when this is open, you will have an output, right? So this is again will open here. This one is open, just like this condition. Again, it will be open. So what will happen to the diode when at the entire reverse polarity? This is the negative cycle. This is the positive cycle. This is the negative cycle. At the entire time of this negative cycle, the diode is open, so it will be reflected in the oscilloscope. So all of this has been drawn, and then again it will reach zero here. It will reach zero here, and will reach again 0.7. It will close, diode close again. No output here. No output here when it is closed, and again, so you will have this waveform in the oscilloscope, or later we are going to do it in PSPice. Okay? Now, this is what you call full wave rectification. Full wave rectification. You see here diode 1, diode 2, diode 3, diode 4. Look at the polarity here. This is the positive, negative, and here this is the diode 1 here. Negative, positive, and then this is positive, negative for this D3. Now, during the positive cycle, what will happen? During the positive cycle, so I have a cycle here, positive cycle. During the positive cycle, so this is which diodes are open. Considering that this, let's say for example, this is ideal diode without considering the threshold, ideal diode. So during positive cycle here, this diode is open, is closed, this is open. What else? So if this is open, this is shorted, let's say, let's use the word shorted. If this diode is shorted, then there will be a current flow on this direction. This one also is shorted. Okay? Okay, look at the current direction here is going to from this point to this, from right to left. Okay, current direction. This is during the positive cycle. Okay, just like here, positive cycle. Okay, this is shorted and this is shorted. So the current, look at the current direction here, it's going there, right? Now, during the negative cycle, so negative cycle, if this negative cycle, it will be on the opposite direction. So this diode now here will be shorted. This diode here will be open. So this current direction is here. This current direction is here, and it will go down. And it will return, right? Notice that in both cases, the direction of current here is from right to left. Here, the direction of current is right to left. So when you plot the output across this, we are taking the output across this resistor, right? R. So it will be positive cycle. Okay, during negative cycle, it will still be on the top, right? Okay, this is the positive cycle, and then the negative cycle, it will still be on the top. That's just like here, right? This is called full wave rectification. As compared to the half wave rectification, you you have half of the wave has been obtained as an output. Here we have both waves are considered. So now, let us now consider a diode which is not ideal. Let's say a silicon diode that the threshold voltage is 0.7. So what will happen to your output? Here, look at this. So if I compare it to the source, so okay, full wave, this is the source, right? Okay. So here from 0 to 0.7, this is 0.7. If you plot this one here, if you plot this vertically here, at this point, 0 to 0.7, no output. You cannot have output here, because all the diodes, this diode is open, no current flow, and when it reaches 0.7, it will start to close, so the current will start to flow here, and it will reflect the positive cycle up to here. And at this point now, there will be at less than the voltage of the source will be less than 0.7, so the diode will be open, right? Because not enough threshold voltage. So that's why you have at this point up to here, and up to here now, this negative 0.7 here, this point. So this is positive 0.7, this negative 0.7, right? Negative 0.7 at this point. So the distance from here to here requires time. Okay, at this point in time here, it's now greater than negative 0.7. Again, it will be reflected on the output, because you know, as I said, the current direction are both on from right to left. So to calculate the DC level of the output signal of this waveform, that we have to use BDC is equal to 2B max over phi. Okay? Okay. There is what you call actually peak inverse voltage. It's the maximum reverse bias voltage rating. Typically, the peak inverse voltage rating of a generic rectifier at least 50 volts, right? Or you can obtain it from the manufacturer's specification, data sheet. So what does it mean, peak inverse voltage? So this is my diode here. I have a source which is reversely connected to the diode. The diode here, this is the negative terminal of the diode, this is the positive terminal. However, I put a positive here. So what if I keep on increasing the voltage, of course the diode, the current is very small, and after some time there will be a leakage current around very, very small, 50 micro or 20 microampere for silicon. And then after that, if the voltage here is too high, okay, the diode will break down. So it will break down. So what will happen after? It can no longer control the excessive current. So what will happen here? There will be a vertical avalanche current that will be reflected here. So the shorted, it's like a very high current. Immediately, very high current will pass because you had reached the more than the peak inverse voltage or the maximum reverse bias voltage. Okay, and here this is the plot of the forward bias here. Okay, at 0.7, let's say at 0.7 here, 0.7, it will start to conduct current. Okay, this is I and this is the voltage. Now, how to build this in our breadboard? So we have a diode here, 1, 2, 3, 4. Look at the orientation. Okay, we are going to connect the output in this side and in this side, and our ground of the source to be connected at this point. Okay, so what will happen? This one is positive. Okay, and then after that, it's more than 0.7. It will have a flow here. It will go there. Okay, and it's continue. It will go here. It will come there. Right? So how to obtain the output? As you can see, this is the source. Again, this is the ground. But all grounds out together. Channel 1, we connect the positive or channel 1 into A. And we connect the negative of channel 2 into the same polarity as the ground, same ground location. And we connect the positive of channel 2 into B. So what will happen? The oscilloscope has a math function. Math function, I'm going to choose to show you later in a practical video. It will be, we can use channel 1 minus channel 2. Then we can obtain a full wave rectification. Okay? So sometimes, if we want a better DC output, so we have to put some capacitor. So look at this one. The capacitor at this point, this is the capacitor voltage. While it is on our this cycle, it's going down. The voltage is, so the output here will be this one. This red line, this is the output with depending on the value of the capacitor.